Let's talk about how one neuron's many inputs combine to either generate an action potential or not. If a large enough voltage change occurs in the postsynaptic neuron, it will trigger an action potential by opening all of those voltage-gated sodium channels. There's some threshold membrane potential that needs to be reached in order to trigger that action potential. The exact value of that threshold will depend on things like the types and densities of specific ion channels in the cell membrane. The postsynaptic neuron will be brought closer to threshold if it receives many excitatory inputs at once, and farther from threshold if it receives many inhibitory inputs at the same time. You can think of all the signals that a postsynaptic neuron receives around the same time, say within a few milliseconds, as being added together to reach threshold or not. For example, imagine a neuron with a resting potential of -70 millivolts and a threshold of -55 millivolts. Each excitatory input changes the voltage of the membrane by +5 millivolts, and each inhibitory input changes the voltage of the postsynaptic membrane by -5 millivolts. If this neuron were to receive 3 excitatory inputs at the same time, it would reach threshold and fire an action potential. Just 2 excitatory inputs alone would not be enough to reach threshold. Similarly, if the neuron receives 3 excitatory inputs and 1 inhibitory input around the same time, it won't reach threshold. In reality, the scale on which this addition is happening is usually much larger than in this simple example. Excitatory and inhibitory synaptic inputs are typically coming from hundreds or even thousands of presynaptic neurons. Each neuron is performing a kind of computation or sophisticated comparison of its many input signals. The specific computation performed will depend on the neuron's connectivity, its intrinsic electrical properties, and also the neurotransmitter and receptor expressed at each input synapse.